So thank you for coming. This talk is covert debugging, circumventing software armoring techniques. My name is Danny Quist, co-founder of Offensive Computing, PhD student at New Mexico Tech. I do reverse engineering, exploit development, and member of CDC NSF.
Hey, how's it going? I'm Valsmith. I'm one of the co-founders of Offensive Computing. I do malware analysis, reverse engineering. I'm also a contributor on the Metasploit project, do pen testing, and part of CDC NSF. So just real briefly about, so those of you who don't know what Offensive Computing is, we're a small company that does malware analysis. We provide free access to a large database of malware samples, about 160,000. I believe we have the largest open malware collection on the web, at least it's published openly. We provide a few business services like custom malware analysis, malware data mining, targeted information for malware, and reverse engineering.
Okay, so this talk is about debugging malware, and specifically tracing its runtime. We want to monitor API calls, and we want to get to this area where we can do dynamic analysis across a wide range of them, because that provides us with automation for automatic analysis. But the point is that malware is getting really good at preventing it. A lot of the packers are pretty clever about doing things. They detect whether you're debugging them. It's trivial to detect VMs of all types and variety. And these were techniques that were originally pioneered by legitimate software trying to keep crackers out. So what we're going to talk about is the general techniques of software armoring, go over some of the requirements. We'll talk about two methods. The first one is dynamic instrumentation, and the second one is going to be a page fault-assisted debugging method. And as an application, we'll show our generic auto unpacker and the results of that. And so Val's going to talk about software armoring.
Okay, so this is just sort of some background information on different techniques that software uses to protect itself from analysis. So I'm going to run through a variety of techniques, some manual demos before we get into our new stuff. So there are several ways that software uses to protect itself from analysis. Some of the most common are packing and encryption, SEH tricks, virtual machine detection, debugger detection, and something called shifting decode frame. And I'll go in depth into each one. So packing encryption is generally where you take another program, feed it an executable, and it will compress it or encode the instructions in the binary. There'll be a small decoder stub at the front of the binary, which contains the instructions for how to decompress or unprotect it. It'll do things like restore the import table, which we'll get into more later. Also, it can play tricks with these portable executables, the file format that Windows uses, like hiding the imports table, obscuring relocations, encrypting, compressing the executable. So this is kind of what a normal PE file would look like if you're looking at the sections. You can see up there on the screen some clear text, understandable assembly instructions, some calls to different functions. And this is what a packed or protected executable will look like. Pretty much gibberish. You can't understand what that is up there. And then there'll be a little bit of instructions that tell the program how to decrypt itself. The next technique that binaries use to protect themselves from analysis is something called virtual machine detection. And we talked about this at Link last year at DEF CON. There's a whole bunch of different ways of doing this. One of the best ways is a single instruction detection using things like the descriptor tables. There's a bunch of tools out for this. Joanna Rutkowska made something called RedPo, which is pretty great. Another tool called Scooby-Doo. And last year we released a tool called OCBM Detect. And this basically relies on the fact that there's instructions for privileged and unprivileged CPU mode. Virtual machines try to be efficient, but not necessarily secure from the point of view of hiding or being stealthy. If you want to learn more about that, go to Joanna's talk. They don't fully emulate x86 instruction set or architecture bug for bug. So the next set of protections is called debugger detection. And generally, when you're analyzing a malicious file to see what it's doing, you'll put it in a debugger and step through it and try to see what API calls are made, what's going on. So what a lot of malware authors have done is try to detect that and then take some action to prevent you from doing it, whether it's destroy the binary, cause the debugger to crash, or whatever. There's a variety of things it does. The most common technique that we've seen is something called isDebuggerPresent, and this is a native API call to Windows that you can use. It checks the process execution block for the magic bit. You can hide from this really easily. There's all the debug plugins that let you hide from this. So there's a lot of ways around this, but malware authors still use it quite a bit. Another good way to detect if you're being debugged is a timing attack. One way of doing this is issuing the RDTSC instruction so that you can check, okay, well, am I running really, really slow? In general, that means I'm being debugged. This is pretty effective. It definitely makes it harder to analyze the malware. So another thing that, another part of debugger detection is things like int3 instruction scanning. This is where you see am I being breakpointed or paused. Malware will also check its own executable to see if it's been modified. Hardware debugging detection, looking at CPU flags to see certain signatures that indicate that we're being debugged. A lot of people used to use a tool called Soft Ice for doing binary analysis, and it's a pretty good tool. It's been discontinued, and there's a lot of ways to detect Soft Ice. There's a ton out there on the internet. Same things, checksumming, int3 scanning. There's a bounds checker signature that works pretty good for Soft Ice. So another thing that malware does to protect itself from analysis is called SCH tricks. This is basically where the malware will use the structured exception handler in order to unpack itself. And the way this works is the structured exception handler receives an error from a program, passes it to a handler which takes some action, whether it's pop up a window on the screen, or in this case, it's the instructions for unpacking or deobfuscating the binary instructions. So malware will use this actually to unpack itself. The problem with this is that in many cases the debugger will think, oh, well, it crashed, so there's nothing else for me to do, or the debugger itself will crash. There's ways around this. Also, there are plugins for OllyDebug, different settings you can use. One thing we saw recently is a T-lock will actually do divides by 0 to cause an exception and pass itself to the decode instructions. Okay, so one of the other techniques is shifting decode frames. This is where a binary will be encrypted or obfuscated. It'll take little sections of itself, decrypt them, run the instructions, re-encrypt them, move to the next section. This is pretty hard to defeat. There are ways to do it. It's kind of specific depending on the packer. And some people have actually implemented these techniques for legitimate uses, like PatchGuard.
The Meta is another good example of a packer that uses this.
So, but basically the Achilles heel of these protection techniques is that it has to execute. It actually has to run on the hardware. There have to be valid instructions. So at some point you can observe these instructions and tell what's going on. So if it executes, it can be unpacked. So now I'm going to go into sort of the manual techniques. It's a pretty labor-intensive process to deobfuscate software. And I'll give a simple example so you can see how this works. So the way an unpacker works is that there's a write to an area of memory. This is where it begins the decode. The memory is read from, it begins to execute, and then there's more memory that is written. This is optional re-encoding. The main concept here is that the CPU can only execute valid instructions. It can't execute compressed gibberish or encrypted information. So this process can be monitored. Unpacking is basically a function of timing. If you can get to the point where the instruction is being passed clear text to the processor, you can read it, you can unpack it. So there's several stages to the manual unpacking process. The first thing that you generally do is try to identify what is it packed with. Most malware uses a subset of common packers that are available. There are a few that use custom packers. These are often, you pretty much can't identify it. You just have to manually figure out what's happening. The next stage is to find what's called the OEP, or the original entry point. This is the point at which the original software executes after it's been deobfuscated. In general, with most packers, once you're at the original entry point, you have the process in an unpacked state. If you can dump it, you dump the process memory to a file, You can read it and analyze it and see the instructions, function calls, etc. The next stage is generally when you dump to a file from memory, you have to fix it up to make it look like a valid PE file so that you can analyze it with IDAPRO or some other tool. So there's several methods for identifying the type of packer that's being used on a binary. But probably the most common is there's a tool out there called PID, which is pretty good. It's signature-based, so it's got thousands and thousands of packer signatures. The second tool, which is one that we use often, is MSFP-Scan. This is part of the Metasploit framework. It's been modified to actually do packer signature detection, and it uses a similar database to the PID database. The nice thing about that is that you can automate it and script it versus PID as a GUI tool. Also, there's a really great tool from Aero Carrera called PE File, which Danny here has made some contributions to, and we've tested it against a large set of malware to make sure it works very well. Sometimes you can manually look at section names or other parts of the binary and get hints. They'll leave hints in there as to what the packer is. And there's a ton of other scanners which are usually not as good as the above methods, but sometimes will yield interesting results. So this is just a screenshot of various tools detecting what packer type's being used. You can see this sort of little gray box in the middle. That's PID detecting a UPEX packer. In the background is our website detecting a packer as well. And the black window is Metasploit's MSFP-Scan. Okay, so once you've identified what packer type is being used, there are a whole bunch of methods for finding the original entry point. This is probably, in general, the hardest part of the process, depending on the packer. One good way is if there's a ton of Ollie scripts at these websites. OpenRC is a great resource for this. The problem with these is you have to have an analyst running Ollie debug, bringing it up, loading the script, and basically doing all this, so it takes some time. There's also a bunch of tools out there which do OEP finding. They're signature-based, they're specific to certain versions of packers, and they're a little hard to use. Here's an example of a script being run in Ollie debug to detect the OEP of a UPEX pack binary. So the highlighted instruction up there in Ollie debug is actually OEP in this case. Okay, so once you've located OEP, the next step is to dump the process memory to a file. There's a whole bunch of tools for this. Ollie dump is a good plugin. Lord PE is one I like a lot. And there's a bunch of custom tools. But basically, these 4 API calls are what does this process. You open up the process, read its memory, create a file, write it to a file. It's pretty simple. So this is a screenshot of Lord PE dumping a file, dumping a process memory to file. Okay, so one of the most important things to look at to understand what a malicious file or any file for that matter can do, what its capabilities are, is the import table. This is basically a list of functions that are imported from DLLs in the system. Most malware will try to obfuscate this, obviously, because this is how you know what can it do. Can it make calls to the internet? Can it create files, delete files, edit registry? There are a couple of tools for fixing the import address table when it's been obfuscated by malware. The best is probably ImportRec, but again, it's a GUI tool. It's a manual process, hard to automate. This screenshot shows the 2 tools that I know of, ImportRec and a tool called Revirgin, actually rebuilding an import table. Okay, so at this stage, once you've dumped it to a file, you should be able to see clean disassembly, instructions that make sense. The IET should be visible. You should be able to analyze the file and figure out what it does. This process can be